Okay, so this trick is actually harder to write down a problem for than it is to execute. So this is what I like to call the divergence theorem flip trick, which is a little bit like doing a kick flip with the divergence theorem. So what I want to do is evaluate a flux integral where I have some vector field. I just picked x, y, x, y, z was a shit choice, whatever. Pick some vector field, and your surface is the top, left, right, front, and back of a 0, 1 by 0, 1 by 0, 1 cube, right? So this is 5 sides of a cube. You guys all see that? So like, my picture is
it's cube, but
cube,
the bottom is missing.
And this is not there. See this?
Yeah.
So what I would like to do is evaluate this flux integral. And I think to myself, hey, this is a really annoying shape. I don't really want to go through setting up all 5 of these. So let me be lazy and set up 1. And the way I'm going to set up 1 is I'm going to say, okay, so if I had the whole cube oriented outwards, you guys see that?
Yep.
So I'm going to call the whole cube, I'm going to call that W,
Okay.
right? So the integral over the whole cube of f dotted with d area is something to which I can apply the divergence theorem.
Yep.
You guys see that? So as long as this is oriented down, right? You guys see that? The bottom. So I'd have to add the bottom and they're oriented down. And then I could apply the divergence theorem. So I get that this is the integral over the cube. And here I'm using the divergence theorem, right? Of what?
It's going to end up being, gradient dotted with f, which ends up just being 3.
Cool. You guys all see that? You get 3. Cool. D.
dx, dy, dz.
Yeah, d volume, right?
Yeah.
But it's a freaking cube.
And it's a unit cube.
It's 1 by 1 by 1, right? When you integrate a constant function over a unit cube, you get
Constant. The same constant.
the constant. Okay, so is the answer 3?
No.
No.
It's 3 minus.
Yeah, it's 3 minus the flux through the space, through the face you were missing, right? You guys see that? So what I'm really doing is I'm saying, oh, okay. So the integral over W, right, should be the integral over S of f dotted with dA plus the integral over, what was I missing?
Yep.
Yeah, I was missing the bottom, right?
Oh my gosh, every time you get so close.
You guys see this? Of f dotted with dA, right? So instead of parameterizing 5 of these suckers, I can parameterize 1 and then subtract it from 3.
Yep.
You guys see that? So in the end, what I'm getting is okay, so this is the integral over S of f dotted with dA, right? The flux I wanted is 3 minus, okay, now I just need to integrate on the bottom, right? Okay.
So let's see.
So that's going to be a double integral, right?
0 to 1, 0 to 1.
And it's going to be 0, 1, 0, 1. And then this should be your f, right? Evaluated at the bottom. Oh, maybe I should do this. What's the bottom parameterized?
It's like x, y, 0, I think. Yeah.
Perfect. Pretty good with that? Okay, so if it's x, y, 0, then f evaluated at x, y, 0 is
X, Y, 0.
X, Y, and 0. And then you're dotting with,
Negative k. So 0, 0,
you see
negative
that? 0, 0, negative 1, d
1. X, dy.
x, dy, or dy, dx, whatever, right?
Mm-hmm.
And so all told here you get,
You get 0, don't you?
oh, apparently the flux through the bottom is 0. You guys see that?
Yeah.
So you get 3.
Oh.
I picked a shit example because it was the same.
Well,
You guys cool with that? And what's the reason that it's
Wait
the same?
a second.
Oh, because along the bottom, right?
Yeah.
Like on the bottom of your
it's
cube,
0, 0, 0, yeah.
your vectors are x and y and 0, right?
Oh my gosh.
You guys
so
see
it's-
that? So they're flowing
It's
parallel,
perpendicular.
right? And hence they don't go in or out of that bottom face. You guys with me on that? So they're coming like someplace in there, they're through the sides, right? So which sides are they going through?
Away from us, above, and to our right.
Yeah, they're all the divergence in this thing, right? All the flux through this guy is in the right side, the top, and the back, right? Because in the other spots, those are 0.
And there'd probably be one for each face, so.
Because they're flowing along parallel to those faces, so there's no net flux. You guys see that? Cool. So this is the flip trick, right? If you have most of a surface, sometimes you can calculate the flux through a part by flipping this thing over. You can do the same thing with the with Stokes' theorem.
Is that just because of those congruencies and symmetries involved with the cube?
No, this doesn't really have much to do with the fact that it's a cube. It's just that it almost bounded something. Right? So it almost bounded something, and I was able to flip from, okay, what if I had the whole thing, and then the flux through this part and this part add up to the whole thing.
Yeah, okay. So it's just
And then I can calculate one of them easily, and the rest is just whatever's left.
as long as you can chunk it up.
Yeah. Yeah, so as long as you've got almost all of something, you can sometimes like tack on a bottom to get this.
Yeah.
This won't help you with graphs still, right? Because to do a flux through a graph, you'd have to make a shape, right, that bounded something. So you'd have to tack on like 5 sides, and that's worse, right? Like this got better because I took 5 sides and turned it into 1 side. And an easy divergence there. Cool? Okay.